All right, let's get started. So, first I'd like to welcome everyone to Yanni's thesis defense. Yeah, that's right. So Yanni is a much beloved member of the nuclear theory group, and we're all very happy to be here today. So Yanni's going to tell us about his thesis work, where he extended this many-body method called IMSRG, which previously has had much success in describing finite nuclei. He's extended it to describe infinite nuclear matter, such as what we find in the interior of stars. This is a project that has had many ups and many downs. It's been very, very difficult. And I'm extremely proud of the way Yanni persevered, because there have been times where you kind of felt like you were fighting the Greek Hydra, where you solve one technical problem, or computational problem, and two more would appear in its place. And thinking back to where we were, even a year ago, and it kind of felt like saying to the gods, "You got us some slack here." He solved all the technical problems. He built a tremendous framework that future students can build on to address some interesting physics. And in the process of solving these really beastly technical and computational problems, he, in a very creative way, made some connections with another method called Unitary coupled cluster theory as a way to kind of improve the IMSRG method. And I'm just very proud of the way he's overcome the challenges in this project. And I'm kind of reminded of this quote, I think it's by Nelson Mandela. I'm paraphrasing here, but it's something along the lines of, it seems impossible until it's done. And we're at the point where it's done. So good job.
Thank you very much. Okay, so to start before I start, I saw that there's a message. So apparently there's an echo. So I don't think anyone has this thing on that end, just to show that everything is muted. Or just to make sure it's going to be off. Yeah. And just let me know, we'll just say it's a problem, maybe halfway. Okay. So I think we should put it good. Okay. Hi everyone. I'm just going to start. Okay, so just two main. If you really want to get the full scale of it, go and see those slides. There will be supplementary pieces, and also I will be going pretty quickly. It just doesn't matter for the sake of time. Okay, so this is the nuclear matter state, and call it the NM-EOS. And what it is it's given by the total energy of the system of an infinite number of nucleons interacting with each other in an infinite volume. And it's very important because it determines the stability and properties of nuclear matter, so it has a lot of applications to astrophysics. Likewise, the tightly constrained NM-EOS allows for the testing and improvement of the approach models. So we're just going to go back. Two more parts to it. So first of all, these are all the little nucleons interacting with each other. So first of all, we have to have a way to describe how those nucleons are interacting with each other. And then once we have that, we need a many-body framework to be able to say what is the total energy of that system given these interactions. So thanks to Stephen Weinberg, 30 years ago, we have something called high-performant field theory. And what it means is that we have a wide range of nuclear interactions that are available to us that we can use. Likewise, there's been an explosion of many-body methods, particularly perturbation theory, and non-perturbative methods coupled together, and
IMSRG, which had allowed us to be able to simulate systems with a large number of particles, like it's heavy nuclei. And as you see, just over the past 20 years, there's just been a massive explosion in terms of the number of liquid we simulate. And these methods, one is really dear to our hearts, which is the IMSRG manufacturing. So the IMSRG is our little baby here at the. I'm just gonna come here. Easier. Okay, so the IMSRG is our baby here at MSU. Because it really was developed by our Scott advisor, and also it's been pioneered by one of our professors, Michael Burkett, and it's a wonderful method. However, it has not been applied to do realistic nuclear matter equation state studies. So that's what we're going to do in this work. So we're going to extend it to realistic nuclear matter using multiple nuclear forces. And to do that, we're going to have to tackle some of the computational challenges needed to be able to do that. Sometimes it works, sometimes it doesn't. Okay. I'll just be like, okay.
All right. So
to understand the IMSRG, just to understand the SRG, and we're just trying to get the flavor of what it is. So we have a Hamiltonian that we have to describe this system that we're working in. It's composed of 1, 2 Many-Body interactions. And what we want to do is that in SRG, we want to do a sequence of continuous unitary transformations of that Hamiltonian. We want to preserve the energies, the eigenvalues of that system. And you can cast that transformation in terms of an ordinary differential equation here, where you have this thing, which I call a driving force, called a generator. And it's chosen such that you drive the off diagonal parts of this Hamiltonian to 0. Because that's what you want diagonal class. The thing to notice here is that when you solve this evolution, you know you started with 3 body forces and you stuck to 8 body forces in your system. And evolving 3 body forces alone is currently intractable at large scale. So what the IMSRG does is that it improves on the XRG, and it does that by writing the Hamiltonian exactly into a non-ordered form based on some of this reference state. Here. Okay, I'm not truly not good at this, but okay. But you write the Hamiltonian exactly into its non-ordered form, and the main point about this is that just that you can take away from this is that by doing this, these coefficients here, E, F, and these, they're given by all of these contributions where they can feed the body forces into the lower rings. So we work in an IMSRG truncation scheme where we, after we order it, the body force we eliminate it because we cannot evolve it in the flow, but we feed it back to the lower rings here. So just to give you a better understanding of what we're doing. So if you represent the Hamiltonian in a basis of Slater determinants, which correspond to excitations beyond this reference state, or goal excitations beyond this reference state. So this is your original Hamiltonian that you're working with. Actually, I just realized this will help me. This will be much better. There. And I can see the line. Okay. So if this is the Hamiltonian that you have, so just starting Hamiltonian that you have, and you can see it's not decoupled from the particle two-hole excitations. Then when you do the IMSRG evolution, you can transform the Hamiltonian into a form where you decouple the two particle two-hole excitations. And since the reference state is decoupled from all the other excitations, then that means we can just read off the ground state energy from this. So that's what gives us the zero temperature equation state. So just to give you a flavor of what's happening is that as you're moving along the flow, so what you're seeing here is the ground state energy that we're computing. As we move along the flow, it converges through the IMSRG. And also what we do is we include
I'm also showing the MBPT2 corrections. And the point that if you just want to get across, if any of the things I've said make any sense, is that really what IMSRG is doing is that it's generating a unitary equivalent Hamiltonian that you're trying to diagnose, such that MBPT2 is converged. Like MBPT has nothing to do. That says that you are converged. Okay. So just a quick slide. So what we do, we work on a certain flavor of IMSRG called the expansion of IMSRG. What we do is that we can cast that differential equation into another form, where effectively what we do is that we parameterize the unitary transformation we put together as an answer is exponential. And this omega is given by some complicated expression. And the main point of this is that by doing this in this way, we can actually compute a variety of observables just beyond energies alone. So you can compute energies much beyond energies, and also this is very memory efficient because you can use a crude Euler and also it's reminiscent of unitary cluster, which is inspired from the generator we see in the model. So we have four physics objectives here. So we want to be able to calculate an NM-EOS using covariance of the number of type fractions. At the same time, we want to use multiple chiral Many-Body forces, and also we want to lay down a groundwork for a lot of very exciting neutron functions. But to be able to do this, we have to tackle computational challenges to be able to do that. It's absolutely essential. I'll just list a few. So first, we need to exploit the symmetries of IMSRG algorithms as much as we can. Also, we want to be able to cast concentric fractions and just multiply as much as we can. Those are very already optimized. And also, we want to be able to accelerate the IMSRG convergence because you see that the computational velocity on the IMSRG scale is very expensive. It takes a lot of time. So we want to accelerate those and see some of the performance, which is by generators, and also in terms of Shanks and pitch operators. You can see the difference for those. Okay, so the question is how do we actually model nuclear matter? Here, well, what we do is that we place a bunch of identical protons and neutrons into a box with periodic boundary conditions. So our states are given by plane wave states normalized to bonds. And this is just an example of a basis. We're skipping this. Okay. So now great. I'm to say we have shown we've written nuclear matter just out of nowhere. We have this nuclear matter code that's very has one of these great things. I'll just list a few. So this nuclear matter code is compatible with asymmetric and symmetric matter. It has a variety of Many-Body forces, and also it has the Okay, yeah. So I was busy trying to claim one of the great things we've done. Okay, great. So I'm just going to highlight a few things. So the code, first of all, it was written with a lot of care. It is extendable to a lot of other systems, so other people can use this. It's integrated with a wide range of power interactions, and it's very fast. Also, it has data compilation tools, so it makes it data is accessible to everyone, which is very important. So the question is, how do we make this code performant? How do we get it to be able to do the things that we need to do? So I'm just going to give you a flavor of some of that. So first of all, we work with anti-symmetrized operators. So for example, if you just look at a two-body operator, there are certain symmetries in that operator, and we know that we don't have to actually store all of that operator because we can recover those sectors through those symmetries. So that just gives us automatically a factor of 4 memory compute. Also, if you look at a given particular, if you just zoom into this operator, you can see, you can recognize that Hamiltonian also conserves certain things like there's momentum conservation, there's net charge conservation. So we can actually exploit that and only store blocks that actually correspond to those symmetries and not store zeros that we don't need. Likewise, when we're doing particle hole. When we're doing commutators, we have to do tensor contractions. And those are really the things that are dominate the program's cost. So one of those contractions, one of the most expensive ones, is in this form. We don't have to worry about what these indices mean and what this means. Just the main point is that this is not in a form that is directly written in matrix multiplication. So you have to rewrite it in a form where it can be written in matrix multiplication. You can do a set of transformations called the particle hole transformation, championed by Heiko Herget. The next thing that from this is that you can actually offload a lot of performance to BLAS and MKL to do those things for you. Just a few quick things. We can also do more optimizations on top of that. So if you have a distinction between particles and holes in your system, then you can actually write your occupation matrices in such a form where it's 0 in all the other sectors, but it's non-zero in one sector. And when you do that, you can actually pre-compute this matrix product that you're doing partially. So, which is very nice. And also, if you recognize there's certain symmetries in our operators, in the Magnus operator, particularly that the Magnus operator in the sectors that do not conserve particles. So, for example, like the sectors that go 3 holes, 1 particle, or 1 particle, 3 holes. Oh, yeah, 3 holes, 3 particles, 1 hole, 1 particle, 3 holes. Then actually the Magnus operator is 0 in those sectors. So that means you can actually just eliminate this part of the matrix multiplication. You don't have to worry about it. And likewise, you can do similar in the Magnus expansion. So, and furthermore, I'm just going to quickly go through this. You can do even more optimizations on top of that. So you can realize that these blocks of these products actually conserve relative momentum. This thing is in the way. I kind of feel like I shouldn't even touch anything. But the point is that these blocks conserve relative momentum and relative charge. And you can just store those blocks. And if you use something called, I call mirror block symmetry, you can actually save a factor of 2x compute in memory in these matrix products. You can actually recover them from symmetries. Okay, great. This part I'm just going to skip. There's no time. Okay. If you have questions about cache and stuff, actually, we can talk about it afterward. Okay, so just to get to the performance results. So we're just going to show what the general scaling is for the IMSRG, just to see that we can actually do calculations. And just the main point here is that, so we're plotting the total runtime, we're plotting the amount of time it takes to do the commutators in the program. And what we see is that the commutators are the leading cost of the IMSRG. And that's exactly what you want, because the commutators in theory should be the leading cost of the IMSRG. And they're very optimized. Also, this plot was generated by the data handlers. So everything here is totally automated. Great. Okay, this part, just the main point is that we're also seeing the same kind of scaling that we expect given the optimizations we made. This is actually expected. You can see more details in the thesis. And this is just to show the memory cost of each of these calculations. So we can easily, so we usually require hundreds of gigabytes of memory to do these calculations at a large scale. We can easily go up to a terabyte. And just to be clear, this is not hard drive, this is RAM. So it's very, very expensive. Okay, so now we want to get to the nuclear matter equation state, because that's what we really care about. This is just the introductory flash of like, okay, we can do pure neutron matter calculations with 66 particles, which is sort of standard in the literature. And I just want to show off, we can also do 1,000 particles, which is not usually done in the literature. However, we have issues of convergence in terms of the number of orbitals that we're using. We don't know if this number is enough. We need more than that. But it's just to show this is the gains you get from all the optimizations we made in the commutators. Great. So this flash is image is just for, it's just to give you a sense of actually the computational cost of what we're doing here. Don't worry about the physics yet, we'll get to this part. This is the EOS with electric nuclear matter with the anti-microlide Nozick interactions, EMN. The main thing to focus on here is that we generate these plot, it took 11 days and nearly a terabyte of memory. Okay. I think it's important to show these plots because these things, they affect climate change and they cost money to do. It's not trivial. Okay, so just starting off, we just want to show that we can do asymmetric matter calculations. So this is with a proton fraction of 5%. And just a few things to notice. So first of all, we're looking at the Hebler interactions. And these are interactions that have been evolved with the SRG to make them softer. So what we see is that comparing it, we include IMSRG2, but we also include MBPT3, and we see great agreement between the methods. This is expected because it's not too far from neutron matter, which is known to be very convergent. Sorry. Okay, and also, so now if we go to pure neutron matter, so 0% proton fraction, what we see again is that there's, excellent agreement between IMSRG and MBPT3 is boring. Going to the EMN interactions, these are much harder. These are not SRG evolved, they're not solved. In pure neutron matter, we still see excellent agreement between IMSRG and MBPT. So again, boring. Okay, but now we start going into symmetric nuclear matter, and that's when we start seeing deviations. Not that big, but still noticeable. So there are a few things to point out first. Okay, so first, what we're plotting now is we're including MBPT3, but we're also including MBPT4. I'll get to this one later. We're including couple cluster with doubles, and couple cluster with doubles and approximate triples. The reduced version of MBPT4 is effectively, you can get that by doing a diagrammatic analysis, or not just, it's already been done by Scott's previous student, Titus Morris. We do a diagrammatic analysis of couple cluster and IMSRG, and you can see at fourth order, couple cluster and IMSRG, they miss certain diagrams that MBPT4 has. So this reduced MBPT4, we're just subtracting those diagrams that they miss. And what you expect is that reduced MBPT4 gets closer to its IMSRG, and likewise CCD. And that's what you see. But yeah, you see great agreement between these. And the thing to notice also is that the IMSRG2 is between CCD and CCDT. This is also very important because this is actually has been seen in finite nuclei. This is actually what we expect. Okay, so going on to still the Hebler interaction, with actually less SRG evolved. So that means that it's actually harder. This is a harder interaction than the one I just showed. And what you see, when you start seeing is a much larger difference between the methods. You start seeing a lot more disparity. Just in the interest of time, just focus on the main thing here is that, again, what you see is IMSRG2 is between CCD and CCDT. And again, that's what you expect to see in finite nuclei. Actually, a lot of these trends that we're seeing, we can explain it. We actually understand this. I'll get more to that. So now if we go to the EMN interactions, now with the 500 cutoff, it is not an SRG evolved interaction. So it is not solved at all. It's very hard. And what you see is a much larger spread between all the many-body methods. The main point, again, IMSRG2 is between CCD and CCDT, but also I just want to say, we using perturbative analysis of these methods, we actually understand why we're seeing such large disparities between these methods. And we think this is due to non-perturbative physics. I mean, partly if you do the comparisons to MBPT between the methods. So we think it's due to non-perturbative physics. So the key takeaway is that you see excellent agreement in IMSRG and MBPT in pure neutron matter, boring. Okay, but you start seeing sizable disagreements in symmetric nuclear matter with the harder forces. But these disagreements are understood using perturbative analysis of couple cluster and IMSRG2, which is from the work of Scott's previous student. And okay, IMSRG2 and these, they fall between couple cluster and CCDT. Great. I think I made, okay, I'll just quickly say these. Okay, and these methods tend to saturate near the same point, which is good. And triples, if you notice, the effect of triples, if you compare CCD and CCDT, it gets bigger as you increase the density. So that encourages us to wonder about if we need to include triples in the IMSRG2. All right. So the point is that all of this stuff I just showed you is that the EOS is very expensive to generate these plots. So this is the motivating idea for wanting to accelerate the IMSRG. So I'm just going to sort of just guide you through this. Okay, so at every point in the IMSRG evolution, we have to do a unitary transformation on the Hamiltonian we're trying to diagonalize. And that transformation is given by this thing called the BCH expansion, which I write here. And what you're seeing on the y-axis here is that you're looking at the norm, the off-diagonal norm of the nth partial sum of this sum. So for example, the 0th order part of the sum is this term. The first partial sum, so the 0 partial sum is this. The first partial sum is this. And you can see that here on this, and so on for the higher orders. Okay, so the main point is that as you go further in the IMSRG evolution from S equals 0 to later flow, what you see is initially the Hamiltonian is not diagonal, but towards the end of the flow, the Hamiltonian becomes diagonal, which is what you expect. But the key point is that, so if you notice, the Magnus operator from IMSRG is actually a great UCC solver at order 3. So if you just use that Magnus operator at order 3, it would eliminate a large part of the off diagonal. And better yet, if you went to like order 5, it would be effectively 0. So what you want to do, the idea is that you want to be able to solve, if you can solve unitary coupled cluster at a lower order, then you can actually accelerate the convergence of the IMSRG very quickly. But you still have to deal with this higher order stuff. But the issue is that the higher order stuff is very nonlinear, and whatever errors you make can really cost you. So you just want to rely on the Magnus operator to improve on that for you. So that's just a general idea of what I'm trying to do here. I'm actually more ambitious than that, but it's just to get the flavor of what's going on. So these other slides are just to reinforce what I just tried to convey to you. And you can see them if you want to. I'm just going to skip them. Okay, so I told you what IMSRG is, but I didn't tell you what UCC is, really. But the point is that in UCC, you're doing this unitary transformation. You're trying to generate an eta such that the off-diagonal part of the Hamiltonian is 0. And again, we saw this expansion, the BCH. We just showed it. That's what that amounts to. And if you recognize the linearity of these commutators, you can actually rewrite this expression in this form. And just the main point to take away from this is that if you assume that this HRG is approximated or known, then the question is, can I just invert this commutator, since this HOD, this H here is known, can I just invert this commutator to get the eta? And that's really what we're going to try to do. Okay, so now we're just assuming this HRG is approximated, okay? So then we go here. So this is effectively the problem that we're trying to solve. This is approximated, this is known, this is unknown. Okay, great. So now I'm just going to claim that under some assumptions, you can rewrite this equation in terms of 1, 2, 3, 4. In terms of this way. That's exactly the same as this equation. And if you just adopt this following notation, they call a star, the point being that if you see a star next to an operator, it means that you did a coefficient-wise division of an energy denominator. This equation up here
can be written in this form, nice form. And this form is very reminiscent of the Lippmann-Schwinger equation, but just in operator form. And that has a solution thanks to one of the founders of quantum mechanics, Max Born, who posed a perturbative solution to that. And that's also a solution here. Right, I forgot to mention something, but it's okay. Pretty cool. Okay, so just quickly, so again, so what we've done is that, just to be clear, we inverted, the whole point of why we did this was we're just trying to invert this commutator. Okay, that's what we're really trying to do. And just quickly, what we also want to do is to accelerate that commutator inversion when we can. So say we have exactly the same problem again, where we have to invert the commutator, but we have a good guess for what that answer is going to be. Well, if we have a guess, then we can just rewrite this eta in terms of guess with some error. And you can then rewrite this equation in terms exactly in this form. And now what you have is a commutator inversion with eta. And this term here is known. And if this eta guess is a good guess, then the norm of this left-hand side will be dropped, will be reduced. And then your commutator inversion, your Born series, is going to converge a lot faster. Great. Okay, so just a reminder. So we got the Born series to invert the commutator. Now we need to be able to figure out this HRG of eta or whatever. And this is where the three generators that we introduce in the thesis, that's what they do. So in the standard form, this is the expression for HRG of eta. So first, the Born generator, it just assumes that all these higher order stuff don't exist. It just drops them. Okay, cool. All right, and then the UCC Born generator, what it does is that it tries to be a little clever and change the coefficients of this expansion to try to get a better solution, to get a faster solution. So that's UCC Born. And then this Carrier generator, what it does is that it estimates this HRG by iteratively solving this equation, and it converges. See the thesis. Okay. So just to get to the results, so now what we're plotting is the runtime of the IMSRG using the existing white generator, and we're also including the novel generators. And what you see is generally they improve the runtime of the IMSRG. And this is explained if you look at the total commutator evaluations throughout the program of the lifetime of the program. You see the similar pattern that they're reducing the total number of commutators in the program, which are the most expensive things. And just to understand how they're doing this, you can zoom in at this density point here. So we can look at these IMSRG calculations. And if we do, we can, so what we're doing here is we're plotting. So for every single one of these colors, we have a separate IMSRG calculation, and it gives us a certain energy at each step in S. And then we're comparing it to the converged energy if you did the IMSRG with the existing white generator. And so what we're trying to do is just to get an understanding of what's the spread between the final energy of these methods using these generators. And also we want to see if they're accelerating the convergence of IMSRG. And what we see is exactly that. So all of these generators, they work faster, and then using the YNP generator, and also the spread between the methods is 10 to the minus 3 MeV per particle, which I consider to be great. So just to drive so this is our most favorable result. That was the previous was the least favorable result. You see a similar kind of behavior, but just more exaggerated. You see a significant runtime improvement, and this is due to commutator reductions. And if you zoom in again at one of these density points to look at the convergence profile of the IMSRG, what you see is that there's a significant convergence acceleration using these generators, and with a little spread between the final energies. Likewise, just to point it home again, is exactly the same story. You see runtime improvements, and again, this is due to commutator reductions. Why am I messing up? Due to commutator reductions, and if you look at a certain density point here, we see again convergence acceleration from the methods. So great, yeah. point is that, okay, so the generators, the accelerated IMSRG conversions, we see around 2 to 4x, sometimes, not all the time, but when they do work, we see 2 to 4x IMSRG speed up. And this other part I'm going to say. Okay, all right, so a summary of what we've done is that we've extended IMSRG to compute realistic nuclear matter equations of state with a variety of at least with 3 chiral forces, but we have access to a variety of them. And to do that, we had to develop a high-performant, really a lot of pain went into it, program to do it. And we made comparisons of the many-body methods that we have, IMSRG, MBPT, and coupled cluster, and we saw disparities that we think are due to non-perturbative physics. The main point is that these calculations were very expensive, so we tried to accelerate them. These calculations can take a lot of time, so we try to accelerate them to these novel generators. And also we applied nonlinear methods, known methods, in a new way to the IMSRG to accelerate them, and you can see the dissertation for more of that. Great. Okay, so the outlook is that what we would like to see that we only worked with 3 chiral interactions in this work, and we would like to extend them to use more than that. And also, everything was at N2LO up. At N2LO of effective field theory. We would like to go to N3LO. So we can use these to also determine EFT truncation errors using the excellent work of Christian Drishler. Also, we're very excited to see possible emulators of the IMSRG using really the excellent work of Dean with eigenvector continuation, really created it. And also Jacob Davison for DMD, dynamic mode decomposition, and also Patrick for parametric matrix models to emulate the IMSRG because again, these calculations are extremely expensive. Okay. So we also look forward to incorporating triples into the IMSRG because we saw this density dependence in coupled cluster for triples. Anyway, great. Also the exciting developments on the horizon by Kong Yu for momentum distributions, correlation functions, all that nice jazz and nuclear matter, and also their finite temperature extension horizon, and this can be used with the work of Isaac Smith. So yeah, there's a lot on the horizon to continue with this. So I just want to thank, so this is the team. Me, Mr. Brown, I just think it's a really funny picture. I don't know why. Kong, you, Christian Drishler at Ohio University, obviously Scott. And yeah, I just want to thank all you guys for this was insane. It literally was. So thank you. I also want to give acknowledgements to a lot of other people. So first of all, I want to acknowledge NSF for funding us. I also want to acknowledge the NSCL Graduate Fellowship because that gave me funding at the beginning, so I didn't have to TA and I could actually focus on the research and help my development. Thank you very much. And Kirsten Tolson, seriously, thank you for that. This work was also supported through the ISER, which gave us the compute resources that we could use to generate these plots in the first place, because you can't run this on your computer. Also, I would love to thank Heiko Herget for all of everything. He gave me a lot of, he may not realize it, but a lot of conversations that we had gave me a rich understanding of what was happening here at times that I needed it. I really want to thank him for that. Also, Dr. David Young, because there was a time when we were trying to use Tau array and he helped us. And also thank you for Carl for creative consulting. So yeah, that's the end of my talk. This is the bibliography, blah, 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 blah. And now questions. Sorry, it went over time when all that kind of stuff.
Johnny, so we'll start as we always do with questions from the non-committee members, and then we'll kick everyone else out, and then the real fun will be.
So first of all, nice talk. You commented on the runtime improvement when you use all these novel generators.
Yes.
Can you comment on the memory usage as compared to the normal one?
It's actually slightly worse. So for example, and this is actually by, okay, that's an excellent question. So this is by choice, the Born generator, you have to use an additional operator. You actually don't need to, but I chose to do that. Okay, so that's an additional operator that you have to evolve, which can cost, in the large scales, those can cost like hundreds of gigabytes for just one operator. So that is very expensive. And for these two generators, you need an additional 2 memory locations. So that's you effectively are doing, at most, you have 3 additional operators that you have to evolve with these. So they actually can, at the large scale, increase your memory footprint. So that is an excellent question.
Thank you.
Could you show again one of the plots showing the discrepancies for symmetric nuclear matter backwards from different methods?
Symmetric. So any one of them.
Yeah, any one of those with nice big differences.
Yeah.
Yeah. So if everything below saturation is unstable, it's negative pressure, and in reality, what would happen is the energy, because you have no Coulomb, so the energy per, I assume you have no Coulomb, so the energy per particle would be at the minimum. You know exactly what everything below saturation should be. But it should, if you really had all correlations and fluctuations, you would just have one big drop of saturated matter and vacuum, either bubbles or drops. Okay.
Okay.
If you really had the perfect many-body solution. So I can understand why methods with different handle clustering differently would differ a lot, especially below saturation, because in a sense they're all wrong to different degrees. But I'm really surprised by how much they differ above saturation. Do you have any idea about physically what's going on? Maybe it's not clustering.
Physically, no, but I can. So the answer I can give you is not fully satisfactory. Physically, I don't have. I'm sorry, I don't have an answer. But so first of all, the difference is, so say for example, you're looking between. Okay, the point is that so you can do perturbative analysis of these methods. Again, so these methods are non-perturbatives. And what I mean by these methods, I mean coupled cluster and IMSRG. But you can expand them out and do those analyses. And you can see that when you do that analysis, for example, say you compare CCD to CCD to IMSRG2, what you see is that IMSRG2 actually undercounts certain diagrams in CCD that are very repulsive. So the point is that, okay, so that's just the first part. IMSRG undercounts those diagrams. And then 2, if you look at CCDT, it incorporates triples, which tend to be very attractive. So the point is that why you would see this discrepancy is that, so first of all, so IMSRG2, again, it's sort of like it's undercounting those repulsive correlations. So it tends to be more attractive than CCD. And likewise, both methods tend to be more repulsive than CCDT because they don't have the triples. So the point is that there seems to be, at least we understand, like just at fourth order qualitatively, why we would see such disparities between the methods. But why is it that there's this density dependence? I don't fully know at higher densities, but what I can say is that you do recognize, if you look at just between CCD and CCDT, as you go to higher densities, the spread between the methods tends to get bigger. So it seems to be that at the higher densities in coupled cluster, effectively, the effect of triples seems to be bigger compared to just CCD. And that you can understand through because these methods are, if you just ignore the particle hole terms in these methods, they're similar to this thing called Bruckner theory. And you have this thing called this whole line expansion where there's this hierarchy of these methods, and they all come in with a factor that depends on the pretty much it looks like a density. And the bigger that density goes, then you see more of that spread, something like that. But physically, I still have not answered your question. I don't know. But the point is, we do have some ideas of that we expect to see some differences, But why are they so exaggerated, especially the high density? I don't know. And sorry, maybe that was a long answer.
That's good. I asked you what you thought, that you answered exactly what you thought.
Yeah, that's what I have here.
I'll just add that for the perturbative faults, you can, the number of diagrams explodes. I mean, that's why perturbation theory is asymptotic, right? And when you start looking at the individual contributions, they're individually large, they're fine, delicately canceling. So I think you really are seeing kind of the onset of, that breakdown.
There's assumptions in like the interaction and orders of perturbation theory, but there's often in many methods, there's an assumption about how many, what's the order of the clustering that you include, like 3-body, 4-body in the trial wave functions and stuff.
Yeah.
Okay. So you're saying there's a hierarchy in terms of this?
Yeah. So
That's the whole line expansion, right?
That I would thought would make a big difference, that the low density and the high density I would have.
Okay. No, so by clustering you meant, okay, yeah, low density, but here.
But I don't, that wouldn't explain anything. I don't think.
All these methods are based on expanding around a uniform reference state, so you're never going to get like real clustering. Yeah,
they're all equally bad there.
Yeah.
My only thing to add there is, we're only working single reference, which is what you just said.
Yeah.
Pablo or something like that. Yeah. Right.
Yanni, excellent work and awesome presentation. Thank you. I have two questions. The first one is, with all of this discussion, if I understand correctly, you have two things. You have the interaction rules, and then you have the many-body method that you're using to apply that interaction. And here we're looking at fixed interaction, changing the different many-body method. Make sense?
Yes.
Would it be possible to try to shine, to put some light into what Scott was asking, to choose an interaction rule that is so simple that you can know without, like you have an answer that you can maybe figure out with pen and paper, and then apply these methods and compare what the methods give you to that simple thing, try to understand why they differ in the way that they differ. Is that possible or not at all?
I mean, it's certainly possible. So for example, this nuclear matter is very similar to this thing called electron gas.
Okay.
And in electron gas, you have the interaction is given in a form, it's analytic, and you can do integrals and everything, and you can do it on paper. I don't know if these methods have been compared there. It should be possible. But in terms of here, I guess you could try to write something down, and then you could have yeah, I don't know. I don't know if you can have an analytic solution here. That I'm not so sure, but you could certainly, in a different system that's so similar to this, do something like that. And I don't know if that comparison has been made.
Okay, would be interesting. I always recommend that when people are puzzled with something, is like, can you narrow it down to the simplest thing that you can do to then figure out? And the second question is just on my ignorance. You were mentioning when you were talking about the interactions that, oh, this one is harder because it has not been IMSRG evolved. I didn't understand that. Could you?
Oh, that's just fine. Okay, so there's these things called the Hubler interactions. Not just Hubler, it was also a homeboy.
Okay. Hubler and homeboy.
Several other
And several other homeboys.
Homeboy,
But anyway, so the main idea is that you start off with a REFT interaction that is, you haven't manipulated it. And what you're doing is effectively, you're using the same idea of the SRG, which is the point of the SRG is that you can actually pre-process the Hamiltonian into a form where it's more convergent in terms of, for example, perturbation theory. So you're not using the IMSRG to solve it, you're using this thing called the SRG to solve it, where you're doing it in free space. And it's just a way of transforming that interaction into a form that is soft, that is, it makes your many-body methods that use those interactions to be more convergent. And on top of that, you can then use that on top of the IMSRG or any other method you want to use, like perturbation theory, cluster, or anything like that. So yeah, it's just being transformed in a form that it's easier for your many-body methods to use it.
Pull up the house lights Is it possible?
And, if there are no more audience questions, let me ask the people online who are non-committee members, are there any questions? I guess they could unmute themselves if they do.
Oh, I'm saying, would the audio play through? Probably.
Well,
Yeah, this
It's
is
not-
Paul.
it's not-
Can you
Oh,
guys
yeah,
hear me?
yeah. Okay. Hey, Paul. Hi, Paul. Hi, Paul.
Hey.
Sorry, there's an echo.
Oh, there's an echo again,
But
but it's gonna be quick.
Yeah, it's
So
fine.
So it's not a physics question, it's more, so what's next? Assuming they don't torpedo you during the closed session.
I hope not. Okay, thank you very much, Paul. So his question was, what's next? So not a physics question. I want to go do something that I think is meaningful to people, and I want to do something that I'm very passionate about and I can put a lot of energy into. So first thing is I want to go make some money. So do some tech jobs, make some money first, and then use that to kind of springboard into something that I think can be worthwhile and worth the investment. So there's no concrete answer to that, but I'm sort of willing to see where the tides take me. Can you say that again, Paul?
Thank you.
Hello?
Oh, yeah, thank you. Yeah, thank you. Yeah. He said thank you.
Can I? Hello, can I talk?
So,
I have a question.
Okay, yes, okay, you go.
Beautiful presentation.
Thank you.
Uh,
You're biased.
I am. I saw a lot of linear algebra stuff.
Yeah.
Which is great. I'm curious if you could comment on so early in the presentation, you talked about all these different types of optimizations you could use on the matrix, right? And showing the different patterns that you could exploit.
Yeah.
Can you say just a little bit about your process? Like, how did you start identifying all of these types of symmetries that you could exploit to optimize that part?
So that's an excellent question. That's actually a super excellent question. So that came about because I first started. So by linear algebra, I'm guessing you're thinking a lot of these matrix products and optimizing them as symmetries. So that came about because I started writing this nuclear matter IMSRG program when I came in Python, code. And that code was incredibly slow. Incredibly slow. So I spent a lot of time trying to make it optimal. The way I came about these things was effectively force, because I had to. And so I just had to make sure, so particularly I didn't understand the particle hole transformation. Even though the book is very helpful, but I didn't quite understand it. So I tried to understand it, and then once I understood it, then the question was, how can I make it faster? And just to make it clear, I'll give an example. So it's not something crazy, but the point is, like, for example, so here, this is not, there's nothing fancy here. I'm just not saying anything new. This has been established in the literature, which is that, also I'm going to be quick because we have to go on time. This has been established in the literature that you know these symmetries of the Hamiltonian, you can exploit them. But the point that at least one of the points was that, I don't know what that was. Okay. But one of the points is that since you have this symmetry here where you're conserving the net charge, the total charge and momentum, if you look at the structure of these operators here, when you're doing this matrix product, if you just have to sit down and look at them, annoying. But when you sit down and look at them, you can realize that because of that net charge and momentum conservation, you can actually, it manifests itself in this particle hole representation where you're doing this matrix products such that it is actually, again, it's blocked. It's the relative charge and relative momentum conserving blocks. You can see that because of that original structure that you had. So it's sort of just games of just looking for those kind of things, and that's how you get it.
I like games.
Yeah,
Thank you for taking the time to explain that. Appreciate it.
That's all right. Dr. Chris, I think I saw a question. No problem.
Yeah, I have a question. I have a question, but more of an observation. Can I ask?
Yes, of course, of course.
Okay, I just wanted to ask a question about whether it's possible to use steady state for optimization to maybe for future work. Is it possible? Maybe for maybe other. Is it possible to use steady state? Well, I'm saying use metrics, but is there also a possibility for steady states to be used for also for this work kind of work? I'm not sure whether it is them. I remember they use actually two systems, maybe steady state and I've forgotten actually the other names they call it. But is it possible? Whether I wanted, is it just possible? It's not just possible.
Thank you very much for that question. Okay, sorry, this is the process it. Okay, so the question is, can you use steady state solutions in this in some way? So my answer would be no. Primarily because typically when you talk about steady state, that means you're doing some kind of time evolution, which you can work in this frame of quantum mechanics that we do. So effectively, really what we're doing is that we're actually just trying to solve Schrodinger's equation. But we're particularly working in a form where we don't actually work in terms of time. So typically when you're thinking of steady state, we're not solving the Schrodinger equation, with some kind of time. We're not doing any time evolution here. But maybe you're saying steady state in terms of the IMSRG flow. We treat that as a time. And that I don't know.
Okay, no problem.
So,
yes,
yes.
That'll be all.
Thank you very much.
All right.
Okay. If anyone has any other questions, and I'll be happy to answer. What? It's actually 10 o'clock.
Thank you everyone for coming, and it's just Yanni.